Inside a modern data center, thousands of machines process billions of operations every second. The physical density is massive, but the true challenge is timing. Enterprise systems are built on a strict hardware paradox. CPUs execute instructions in mere nanoseconds. Meanwhile, the mechanical storage drives fetching the data and the network stacks delivering it operate in milliseconds. The processors are millions of times faster than the disks. If a CPU had to directly manage the physical geometry of a hard drive, the entire system would stall waiting for the disk to spin. The solution to this speed mismatch is abstraction, completely separating logical data requests from physical hardware execution. This schematic details the data access layer. Application servers see files for sharing or raw blocks for database speed. Below it, storage virtualization organizes physical sectors into logical disks. The OS asks for a file. The virtualization layer finds the bits. By stacking these abstractions, the operating system executes logic at processor speeds, while delegating the slow mechanical execution to dedicated storage subsystems. This abstraction works perfectly for local machines, but attempting to scale this architecture outward by running an I/O-intensive database across a standard distributed file system creates an immediate failure point. Consider a single file request. Data is pulled from the local disk, crossing the internal bus into RAM. The processor then pushes it back out, making a second trip across the bus to the network card, before finally transferring to the client. The mechanical flaw here is routing. Every single byte of requested data is forced to travel through the server's internal hardware buses twice. In a high-volume database, this double handling saturates the system bus and exhausts CPU cycles. The application server stops processing logic and is forced to act as a traffic cop for its own hard drives. To build a cluster capable of massive scale, engineers follow a strict rule. High-volume storage data must be removed from the application server's CPU entirely. But before traffic can be rerouted off the main processor, the physical hard drives must be extracted from the servers and reorganized into specialized groups. Looking at these IBM arrays, we are no longer dealing with local hard drives. Connecting just a bunch of disks, a JBOD setup, provides massive capacity, but the risk of mechanical failure multiplies with every spindle added. Managing that risk requires an intelligent RAID controller. The controller dictates how data is physically distributed. RAID 0, or striping, shatters a data block into fragments and writes them across all disks simultaneously. Read and write speeds multiply, but there is zero fault tolerance. If one drive dies, all data is lost. RAID 1, or mirroring, takes the opposite approach. It ensures maximum fault tolerance by writing a perfect duplicate of every block to a secondary drive. The data is entirely secure, but you permanently sacrifice 50% of your purchased storage capacity. RAID 10 merges the two, writing striped fragments that are instantly mirrored across paired drives. It delivers maximum speed and total redundancy. However, in a data center requiring petabytes of capacity, buying twice the physical hardware you actually need is financially prohibitive. Engineers needed a way to achieve the security of a physical mirror using only mathematical computation. The industry compromise is distributed parity, widely implemented as RAID 5. It guarantees that data can survive a hardware failure without requiring a one-to-one mirror of every disk. This matrix shows the RAID 5 distribution map. The controller stripes standard data blocks across the physical drives, but reserves one block space in the array exclusively for parity data. Parity is calculated using a logical XOR equation. By running the binary values of the data blocks through this formula, the controller creates a mathematical sum. If any single physical drive in the array fails, the controller reverses the math, using the surviving blocks and the parity sum to reconstruct the missing data in real time. The trade-off for this physical space efficiency is a strict hardware tool known as the write penalty. Because parity relies on the exact sum of a row, every time the application writes new data, the system cannot simply drop the bits onto the disk. It must pause, read the old data, read the old parity block, run the XOR recalculation, and finally write the new parity block. This constant background math requires immense processing power. Pushing it down into a dedicated hardware RAID controller ensures the main server processor isn't dragged down by disk arithmetic. The RAID controller resolves physical drive failures and optimizes read-write distribution. But a highly optimized, fully redundant array is still a localized island. For an entire cluster of servers to utilize it, it must be networked. Moving from direct-attached local storage to network-attached models allows dozens of application servers to query the exact same disk array concurrently. Network-attached storage, or NAS, treats the storage array as a pre-configured appliance. It plugs directly into a standard local area network. But NAS systems operate at the abstract file level, using protocols like NFS. Every request must be translated through a file system manager before it hits the disks. In an enterprise database running millions of transactions, that software translation layer becomes a severe bottleneck. High-performance environments bypass this entirely by implementing a Storage Area Network, or SAN. Instead of relying on a standard Ethernet cloud, a SAN utilizes dedicated fiber channel or iSCSI connections. A SAN operates at the raw block level. The network removes the file system manager completely, routing unformatted data blocks directly into the application space with zero translation overhead. Because the underlying hardware rate controller handles all parity and fault tolerance, SANs allow massive application server clustering. The nodes share access to the raw blocks without constantly syncing metadata with each other. A dedicated SAN perfectly optimizes the physical transport of blocks. However, as the application cluster scales to hundreds of parallel nodes, the sheer volume of packets being processed eventually saturates the final layer of the stack, the network protocol itself. At peak scale, maintaining massive throughput is a battle against the CPU. Even with a direct SAN connection, data relies on strict transport protocols. Breaking gigabytes of data down into tiny packets, verifying their delivery, and reassembling them consumes heavy processor cycles. The host CPU spends more time unwrapping network packets than executing application logic. The first countermeasure is the TCP/IP offload engine. By embedding the network stack logic directly into the silicon of the network interface card, the host CPU is entirely relieved of packet processing. The next logical step is Remote Direct Memory Access. RDMA allows an application to fetch block data directly from the memory of a remote storage node. The payload travels across the network and writes straight into the application's RAM, completely bypassing the operating system kernel. By neutralizing the protocol stack and skipping the OS, the hardware path is clear. Data can now move from a platter to a processor without interruption. The final requirement is an overarching software architecture capable of orchestrating this freedom. The pinnacle of this evolution is the shared disk file system. It provides the low-latency speed of a locally attached block drive with the cluster-wide simultaneous access of a standard network file share. This diagram of symmetric virtualization maps out why early attempts at this failed. Both the administrative control requests and the heavy data payloads are forced through a single central point, the metadata controller. The central hub immediately bottlenecks under heavy load. The breakthrough is asymmetric storage virtualization. The system physically separates the metadata control instructions from the raw data flow. On the control path, agent software running on the application server sends tiny, lightweight requests over a standard LAN to the metadata controller. The server simply asks for a file location and requests a write lock. Once authorized, the data path takes over. The massive data payload launches from the disk subsystem via RDMA, traveling across the dedicated storage network directly into the application server's memory, bypassing the controller entirely. Implementations like IBM's General Parallel File System use this architecture to run global environments. System administrators can mount massive distributed file systems across parallel clusters, totally agnostic to where the specific hard drives are physically racked. Abstracting logical volumes from physical geometry, calculating parity in hardware, offloading transport protocols to silicon, separating metadata control from data transit, engineers achieve the ultimate goal of enterprise storage: infinite parallel scale, delivered at the speed of local memory.